organizer for this excellent meeting and for this excellent occasion to come to know Korea. I will speak today about fractals generated by sequence of substitution. This is a joint work with Masayo Mizutani, who started this type of idea, and with Tarek Selami, who is working with me on a PhD. So in some sense, this talk is very related to the previous one, and you could say that the previous one was working on the idea of a shading system coming from the top and trying to find as general condition as possible. And I am going from below, and I am trying to give as particular example as possible. So I think it's important for this kind of topic to have example, and I will try to work out some explicit example with pictures. So I will start by something completely trivial that everybody knows, and which started, but yes, but of course it's not trivial, but let's say it's well known. The Fibonacci word, we start with this game, 1 goes to 1, 2, 2 goes to 1, and then we iterate. There were very nice expositions in several talks. So we take sigma n of 1, and un plus 2 is, of course, equal to un plus 1 un. We go to the limit because all these words are included in each other, so there is in many different ways a limit, and this limit is an infinite word, which we will which satisfies u is equal to sigma of u, which is the fixed point of substitution, and this is starts with 1, 2, 1, 1, 2, 1, 2, and so on. So when you write down this sequence, it's absolutely unclear what makes it very specific. When it looks repetitive, but not so much, and then when you make the picture, it becomes immediately clear, maybe not here. So we translate in picture by 1 is 1 step to the right, and 2 is 1 step up. So we make this path, as Valerie explained in the previous talk. And then when we have this, maybe it's not absolutely clear, but when we make a large picture, we see that this is a line. This is the best approximation of the line, and it is the best approximation in a very precise sense, because if we take the unit square with the upper right corner at the origin, and if we slide it here, then we get a sequence, we cut out a bond, and we get the most primitive, basic quasi-crystal which exists, which is the Fibonacci stair. And this has a lot of nice properties. For example, this quasi-crystal can be renormalized. If you make a shortcut replacing any angle by its diagonal, you get exactly the same combinatorics. You select a sub-window, and you get the same combinatoric for the quasi-crystal. And of course, you can project and get this self-similar tiling. In fact, this can be very much generalized, and the first easy generalization is Sturmion infinite words. And these Sturmion infinite words can be generated by a sequence of substitution, and which is related to the continued fraction expansion. And this, maybe it's better to do it just by chalk. What is the characteristic property of a Sturmion word is that you have a sequence of zeros and 1, and then you take, say, and then you take a window of length n, and you slide this window on the word, and you look at how many different words you see. And the characteristic property of Sturmion word is that P of n is equal to n plus 1, and it's quite classical that this is the minimum possible complexity for an unperiodic sequence. So one thing is that P of 2 is 3 for a Sturmion sequence, But the possible words of length 2, there are only 4 of them. And of course, these two words, these two words cannot be dispensed with, because if you have not 0, 1, once you have a 0, you are stuck, and you can do nothing more than the constant sequence. So these two are obligatory, so you have to choose between one of these two. So for example, suppose that this word is forbidden. This is what happens in this sequence. Then it means that every one is isolated. So every Sturmian sequence is either of type 0, that means 0 can be repeated but not once, there are more zeros than 1, or type 1. But now, this Sturmian sequence, in fact, doesn't contain very much information. Because you see that every time you see a 1, then after that you need to have a 0. This 0 contains no information. So what you could do is to erase this 0. And if you do that, there is a small miracle, not very difficult to prove, it's a very nice exercise, it's that you again get a Sturmian sequence. So you can play the game again and again and again. You will reduce the length of the chains of zeros, and at one moment you will change and you will go to type 1, and then you will start to erase ones. But what does it mean when you do that? It means that this one, you can recover the original sequence by replacing every 1 by 1 0 and every 0 by 0. So if you take sigma 0 of 1 of 0 equals 0, sigma 0 of 1 equals 1 0, and if you define sigma 1 of 0 equals 0 1 and sigma 1 of 1 equal to 1, then you see that every Sturmian sequence can be either written as u equals sigma 0 of v, or u is equal to sigma 1 of v. This if it is of type 0, and this if it is of type 1. And it cannot be at the same time of type 0 and 1. The only possibility would be the periodic sequence 0, 1, 0, 1, 0, 1 with density 1/2. I am cheating here a little if you are looking at one-dimensional sequence, because you could have trouble to recode with the first thing. So maybe it's not sigma 0 of v, maybe it's S sigma 0 of v. But I don't want to. And if you have a B infinite line, which is of course better, then maybe you will have to shift, because maybe the position 0 happened in the middle. It could happen that when you take this sequence, it could happen that 0 is here. So you could have to shift. So there is one special one, very symmetric, which is exactly the fixed point. And then you have the shift of the fixed point. And when you look at this, this is exactly like Penrose tiling. You have the nice Penrose tiling with all its symmetries, and all the other tilings in the space, which are non-countable, and which are in the orbit, but have less symmetries. So this is, for me, the primitive example of S-headic system. And then, when you write this, you can, of course, because V is Sturmian, you can continue, and then you can write, and so on. You can write in a unique way this sequence as an infinite sequence of substitution, and this turns out to be exactly the continued fraction expansion of the slope of the quasicrystal. Well, there is some trouble with A0. It's A0 plus 1, which is the continued fraction, or A0 minus 1, I never knew. But except for that, this is the continued fraction, so it's directly related to the continued fraction expansion. And you have the especially nice case where this is periodic. For example, sigma 0, sigma 1, sigma 0, sigma 1, and so on, which is Fibonacci. Okay, so let's remark that because this limit stabilizes, because I have made the nice choice that every if you take the image of 1, it always starts with 1. So these words are all included in each other. And anyway, I am not really, so you could discuss, because if you take exact, no? If you start from 1 at each step, no? Let's make an example. If you iterate, yes, that's a different problem. If you iterate sigma 0, then sigma 0 to the power n of 0, this is just 0, and sigma 0 to the power n of 1, this is 1, 0 to the n. This substitution is not primitive. These two substitutions are not primitive. What happens is that you have to exchange, and then if you exchange, then it becomes primitive. But of course, if you only goes to sigma 0 to infinity, what occurs? What occurs is that, in fact, you get the sequence with 1, 1, and an infinity of 0. In fact, you should make it be infinite, and you would get this sequence. In fact, what you really get is this sequence. If you look at it like a line, this is the horizontal line. The horizontal line is just 0, but of course, you could think of it as taking a line that crosses at the origin and then making it go to the horizontal, and you will have some not really existing crossing at the origin. Yes, it's just a defect. Yes, and now, if you apply sigma 1 to this one, what you will get? You will get the rational lines. You get all integers and all rational lines. Well, this is trouble. Rational lines are not Sturmian. They are in the thing because of the non-primitivity. And this is why I think that if you make a nice model of Aix-Marseilles system, you should not expect, for example, something like linear recurrence. Here there is no linear recurrence, there is not even recurrence. And for the, now, of course, you will not, maybe not get these, but you will get things with unbounded partial quotients. And they must be there. Most numbers have unbounded partial quotients. So this means the corresponding lines are not linearly recurrent. So we should keep in mind when we are trying to make models, and these models don't work. Well, this one doesn't work so well also. And you can see it in many ways. For example, you can see it, what you are doing here using sigma 0 and sigma 1 is that you are doing additive continued fraction, which it looks something like this, which is a minimum of x over x minus 1 and or 1 minus x and 1 minus x over x. And there is a Gauss measure for that, and the Gauss measure is infinite. And then we get a lot of troubles with this kind of thing. So we can expect these things to occur if we make a reasonable model. There should be some limiting objects which are weaker, like rational element, and then elements which go to this rational model and which are badly behaved. And this is what occurs in the actual models. But of course, we can then restrict to some smaller things, like, for example, bounded partial quotient or periodic point, where everything will be easier. So this is what I would like to imitate. So the first thing that was done already something like 25 years ago is going to Pisot substitution. That is, we choose a substitution with a Pisot matrix. We build a fixed point. We can make weak assumptions to get an easy fixed point, but any primitive substitution has a finite number of periodic points. And go build a stair and project along the direction. So this is a picture that Valérie showed before. We consider the substitution on 3 letters. The canonical one being the Rauzy substitution. And we consider that 1 is going in this direction, 2 is going to this direction, and 3 is going up. So we build a stair. And the Pisot condition is exactly the condition which is needed to have direction. There is always a direction for this stair because this is the Perron-Frobenius vector. But what the Pisot condition says, it says that we stay within bounded distance of the Perron-Frobenius vector. Then, when the idea is to consider this as a kind of crystal and just turn it and look at it in the direction of the Perron-Frobenius vector. So this is the kind of thing you get. This is the prototype of the Rauzy fractal. So now, when we look at this stair, so I had 3 types of atoms, of vertices on this step, depending on the corresponding letter. So I can split the letters as the vertices, as vertices of type 1, 2, and 3 in this example. And now, this set of vertices satisfies a set equation, and the set equation is a very stupid one. It just says something like this. So this will come. This comes again and again. If you write UNA, if you take all the letter A and iterate sigma on the letter A, you get a sequence of words UNA. And now what you can write 2 equations is that UN plus 1A, this is sigma n of sigma of A. So now you apply sigma n to sigma of B, A, which is maybe BC, and you get UNB, UNC. So this is a first set equation. This is a non-trivial set equation, by the way. What this means is that if you look at this stair, and this is first seen as Sturmian sequence, for example, if you look at the Sturmian stair, then this Sturmian stair is built by 2 kinds of edges, horizontal and vertical. But a very much non-trivial thing is that, in fact, you can find 2 very long sets of edges, something like maybe this and this. And you can again build the set with only these 2 elements. This is not trivial. And you will find the same thing in these kind of tilings, in related tilings to Fibonacci, where you can buy 3 very large patches, and the set can be completely rebuilt by using exactly these 3 patches. This is a non-trivial condition. So this is essentially these very easy things. But you can also write instead of writing sigma n of sigma, you can write sigma of sigma n. That is UN plus 1A is equal to sigma of UNA. And this one goes to the limit. It goes to the limit as U is equal to sigma of U. And what it means is that if you look on the stair at vertices of type 1, then each vertex of type 1 occurs inside some image sigma of A. And so there is the vertices. I'm talking about the vertices. I want to have points because when I project, I want to have points. But the vertex is the starting point of the horizontal edge. Yes, I label by the following edge. Okay. So I have this set equation. If you look at vertices of type I, then they can be written as the union of A times the vertices of type J plus some vector for all the possible decompositions. Sigma of J is equal to PIS. That is, when I consider this stair can decompose in sigma 1, sigma of 2, sigma of 3, and so on. And each vertex sits inside of one of these with some vector, which is just the abelianized vector of the prefix. So this is the basic equation for a substitutive stair. Yes? Let's do it really for Rauzy. So I take this one. So I take the fixed point. Fixed point is starting with 1, 2, 1, 3, 1, 2, 1, 1, 2, and so on. So this is 1, 2, 1, 3, 1, 2, 1. So this stair, it starts like this. But now it's made by building blocks. 1, 2, so this is this building block. Then 1, 3, then 1, 2, then 1, then this so these vertices can be grouped in subworlds. And so where do the 1 occur? They can occur as the first image of a 1, or first image of a 2, or and so on. So this is the image of this point by the abelianization matrix of the substitution. The starting points, when you will apply the matrix 1, 1, 1, this is the matrix of the substitution. When you apply this matrix to this term, this point is fixed, this one is sent here, this one is sent here, and the following one, you get a substair done by the word 1, 2, 1, 3, 1, 2, 1, 1, 2, and so on. And you can see, because of the nature of 1, that each starting point is a 1. Then 2 will only occur at the second letter of the image of 1. And 3 will only occur at the second letter of the image of 2. So for example, if you look at vertices of type 3, these are exactly the image by A of the vertices of type 2 plus some shift, which is 1, 0, 0. So this is one special case of set equation, but it's always the case. There is a set equation which is given by the matrix of the substitution. So now, if we take this set equation, we can project it to the plane. And if we look at the projection of the vertices, we get again a set equation. And if we define Ri as the closure of the vertices of type I, by projection, we get this set equation. But now, since it is a Pisot matrix, and we have removed the largest eigenvalue, this is a strictly contracting matrix. So we get what is called a graph-directed iterated function system. The B is the restriction of A. Oh, yeah, RJ, of course, RJ, this is misprint, sorry. Yeah, we have a self-similar system. This is an IFS, but instead of having just one set, we have as many sets as the number of letters. So in this way, we can, this is a well-known thing now. You look at the non-empty compact set of the plane. You have some map which is acting on the compact set of the plane by taking any family of compact set and building a new family. This is a strict contraction, so there is a unique fixed point, and we recover in this way the Rauzy fractal. This presentation allows us to see some nice things. For example, one, if you consider it in this geometrical way, it is very easy to check that there is a weak tiling of the diagonal plane. We take the Pisot direction. We consider the diagonal plane x plus y plus z equals 0. And then we take the fixed point and we project. We get some compact set. But now consider the set gamma of integer point with this condition. This is a lattice in this plane. Now we can shift the fixed point by this lattice. If we shift the fixed point by this lattice, we get exactly all of these three. But this vector is totally irrational. So the projection of these three is dense. So this means that the translate of this by gamma actually covers the plane, and it covers the plane a finite number of times. It's locally finite. In fact, we can, in many cases, prove that it is actually a tiling. In fact, one of the questions is whether it's actually a tiling, and one way to see it is the following. We have taken this fixed point, we have projected, so we get a window. Now, when we get a window, we can build the cylinder over this window. This selects a number of points. The question is whether the points we select are exactly the fixed point, or if there are more points that we have not seen. That is, whether this window is too large or not. Is it exactly volume 1 for this styling or not? But I don't want to go in this direction. What interests me more is that in this way, for every Pisot substitution, we get a nice system, but this only gives a countable number of systems, because this is given by integral condition. We get, in fact, only algebraic systems. With the Sturmion, with the very basic Sturmion example, we have already many more examples. So I would like to go in this direction. So I would like to make a continuous family of substitution. And the idea is to take, as Valérie explained before, a finite family of substitution and compose them and get some fixed point. But now, how can we build this cut and project scheme? Well, in general, I cannot do it, so I will do what I can do very easily. I take two substitutions with the same Pisot matrix on some finite alphabet, which will always have 3 letters. So I just flip the letters. So they are the same word up to some flip. Okay? So now this allows me to build the cut and project scheme because already I have my Pisot substitution, my contracting space, which work for both substitutions. And for example, I will have no problem with primitivity because primitivity depends on the matrix and they have the same matrix. So to make things easy, but this is in fact irrelevant, but it becomes technical, I will suppose that sigma 1 and sigma 2 of 1 begins with 1. Now, if this works, now I take any infinite sequence epsilon n of 1 and 2, and then I compose sigma epsilon 0 of sigma epsilon 1 and so on of 1. And now I get an infinite sequence of words which is increasing. So in fact it's very easy to see that these words un are a prefix of each other, so there is a limit in any reasonable sense, which I will call the fixed word u epsilon starting with 1. And now there is an almost trivial equation, which is that u epsilon, this is sigma epsilon 0 of u of s epsilon. But now I shift. This is not auto-similar. This is heterosimilar. And so that's, yes. So now I get a set equation of the vertices. But this set equation does not relate v epsilon to itself with reasonable definition, but v epsilon to v s epsilon. Okay? And fp is abelianization of the prefix of epsilon 0. So the explicit set equation depends only on epsilon 0, and this depends only on s epsilon. We have separated epsilon 0 and the rest. So in this way, we can obtain, by projection of the contracting plane, this set equation. Well, does it exist? Oh, well, we could build things with prefix, suffix, automaton, and things like that, but there is a better way to do that, is we just consider the whole set of Rauzy fractal. So R is not one Rauzy fractal, it's a parametrized family. This is the map from 1, 2 to the n to the set of family of D non-empty compact subsets of the plane. So I consider all such function with the natural uniform metric. So this is clearly a complete space. And now I define the map on this space by for any such parametrized family of set. I define phi of f by phi of f taken on the family epsilon is small phi of f taken as s epsilon, where phi is the set equation I gave above. That is, I renormalize at each step. So it took me a few, some time to understand how is this working, but now when you have understood what this object is, then there is nothing to say, because this is obviously a strict contraction, so it has a unique fixed point, and this defines immediately all the Rauzy fractal for all the families of all the possible sequences of substitutions. So, of course, I am completely cheating here, because I have supposed that this set equation is strictly contracting, and the one I had for Sturmian sequence is not strictly contracting. And that is where there should be some work to do. But of course, when it's not strictly contracting, it means that there are points where you get problems. So here is an example. So I took the most simple example I could. So since I am a student of Rauzy, I could not prevent myself from taking this one, which is the simplest one where you can play this game. And then now I consider the one which is called flipped Fibonacci or flipped Rauzy. So this is Fibonacci because it's related to the solution, and this is flipped Fibonacci. So these look very similar. They are both automorphism of the free group of rank 3, but they are very different property. This is Rauzy substitution. It's a quasi-disk. It has a rather regular boundary, which dimension about 1.4 for the boundary. And the other one is the one I first saw when I tried to program the Rauzy fractal, because I had made a mistake in the programming. And this is not exactly the same, because this one has infinite fundamental group. It's connected, but not simply connected. And what is very interesting, if you can try to figure out, is that it tiles the plane. It does tile the plane, because it has infinitely many cut points, and when you shift it, then there is some crossing. Yes, you fill the hole. This has interior points. There are interior. It has measure 1, and you can fill the hole by just shifting it. Yes, this is measure 1. And you can see here there is an interior. It's a tiling. It's a tiling. It's slightly difficult to believe the first time you meet this thing. But the boundary is 2, as dimension 2. Yes. It's a perfect set. It's less than 2. Well, maybe you know better than me. But anyway, not the same as before. Much higher than the other one. And now, what we can do, this corresponds to the first one corresponds to the sequence 1, 1, 1, constant sequence 1. This one corresponds to the constant sequence 2. Now I take the sequence 1 and I prefix it with a 2. And when you do that, so this is 2, 1, 1, 1, 2, 1, infinity. This is 2, 2, so it's a bit heavy. Yes, so this is 2, 2, 1, 1, 1, 1. And then we continue adding 2s. And you see that now it becomes disconnected. And even more disconnected. And then it starts to become non-simply connected. And but in some sense it starts to reconnect a bit, and in fact it will tend to the other one. If we play the other game and start with flipped Rauzy fractal, and if we prefix it with 1, then we will see that the connected part will grow, and the disconnected part will become smaller. So this you can fill, and this is 1, 2, 1, 2. This is the sequence 1, 2, 1, 2, which has certainly a different boundary dimension. This is 2, 2, 1. This is a random sequence of length 15, and this is another random sequence of the same length. So you see that you get very different properties depending on what you do. here is another random sequence. So by construction, by the theorem I gave, these these sets, they are not really fractals. It's a boundary which is fractal. These sets depend continuously in the Hausdorff sense on the sequence. But what can we say about the topological properties of the sequence? And for example, connectedness or simple connectedness or things like that. And what can we say about the dimension of the boundary? One thing that is quite clear is that the dimension of the boundary is certainly a measurable function of the sequence epsilon n. And it's easy to check that it is shift invariant, because when we go from epsilon to s epsilon, this is kind of mutual derivation. We just take a finite number of pieces and set them together. This will not change the local topological property. But now take, yes? What? I suppose so. I have not, I want to come back to this later. Now, of course, if you take the Lebesgue measure, the Bernoulli measure on the shift on 1, 2, then the shift is the ergodic for this measure. So this function should be constant. So there should be an average dimension of the boundary. Can we compute this average dimension? And what happens if we, for example, change the weight of the substitution? So already there are a number of non-trivial functions. And much more important, can we play the same game, but now with different matrices? And of course, now this becomes much harder, because we don't really know. We should need to have something that plays the role of the Perron-Frobenius eigenvector, and this is very unclear. So what I think is that if we have really interesting examples, then these examples will not work everywhere. They will work in a large set, but there will be something where you will have something like infinite partial quotients, and it will not work. So, of course, we just started this, so there are many questions which are the same one which already occur for the Pisot substitution, which is, do these pieces overlap? Is the projection one-to-one? Do we get a tiling? And so on. So I believe that, for example, in these examples, since these two substitutions are very well behaved, we can have something like coincidence condition, and probably we can prove that these give tiling, dynamical system, and so on. There is the next example should be, for example, to consider sequences of complexity 2n plus 1, where we have a nice aesthetic system, being that 1 goes to 1, 2 goes to 2, 1, 3 goes to 3, 1, and the equivalent condition for 2 and 3. So in this way we can build a nice set of sequences. This is very natural generalization of Semion sequence, and I would like to end by just showing one picture. So, no, not this one. Yes. If you take these things, then you will get sequences, and these sequences have a frequency of A, B, C, which is very particular, because these are the frequency of A, B, C are given by three real number A, B, C, which the property is that one of these numbers is larger than the sum of the other two, and that when we renormalize, for example, if it's A, then A minus B minus C, B, C, against one of these three is larger than the other two. And you can renormalize infinity often. This is kind of strange continued fraction expansion. In most cases, when you start with a tripole of number, at one moment, you will find a tripole which satisfies the triangular inequality, that is, which falls in the middle, and then you are stuck, you cannot continue the game. So we want to have this set, and this is exactly the set we have here. This is an iterated function system. It's very explicit. It's homeomorphic to the Sierpinski triangle, and I cannot even prove that the measure is 0. No, and I can say nothing about its Hausdorff dimension. Here, you can see that this converges very weakly in 1 over n to the origin. So it's very difficult to get the point here, but it should become extremely black here. And of course, this replicates at all the vertices, and then by the recursion, you get the thing, so it's very black at each vertex. So one possibility, I believe that it has measure 0. This is what numerical computation show, but I have not been able to compute this. For example, if you try, I tried many things. For example, if you try to measure, the problem is that it's very difficult to converge here. So if you just take all this series of rectangle, then the measure of this rectangle is 2 minus pi square over 6. So with such formula, you find that maybe it might be difficult to compute everything. And so either it has measure Hausdorff dimension 2 but measure 0, or another possibility is that it has some non-trivial Hausdorff dimension and infinite Hausdorff measure. I don't know. But this would be the Gauss measure you would need to work with this continued fraction. And then you would expect, when you want to use this aesthetic system, that you have something which works almost everywhere for this measure, for this Gauss measure. So maybe not so easy. So.